All right. So we got our rate law equation, right?
Yeah.
That tells us the rate of the reaction. Now there we found the rate law equation for a very specific reaction. We found it for when we have two things that, like two types of things that collide, right? But I think people can guess from the logic that we had before. If we had the following reaction, where you had something that's like A1 and we have K1 of A1 particles plus K2 of particles of type A2 and like up to Kn particles of An, right? Turn into like something. Doesn't matter what that something is. They can be rearranged in whatever way. If you need all of these to collide at once to get whatever thing, then the rate law. Oh wait, I shouldn't use K. That's a bad letter. Sorry. It's a good letter. We have K. B is terrible. C. If you have C1, C2, Cn, right? This kind of reaction where you have C1 of particles of type A1 collide with C2 of particles of A2 collide, so on and so forth, up to N. Does it make sense what this means as a chemical reaction? Okay. Then the rate law is K, which is our magic constant, times A1 to the power of, the concentration of A1 to the power of C1, times ... An to the power of Cn. Okay, do people agree with this? That we now, for like a general reaction like this, we have this rate law. Now, note that in this reaction, I'm specifically assuming that all of these things collide at once, right? That was a key assumption in our logical when we derived like all the possible collisions. Because if, for example, all of these things collided at once, and then like these things collided at once, and then two of these things collided, actually, it might still give you the same equation, but the logic there slightly changes, and we'll get to that later. So this equation holds only for stuff where all of these things collide together at once. Okay, that's my point. That's what this equation represents. I'm hoping people understand why that is. Okay. All right, that's that. Now I've rewritten that 1, 2, 3, 4 up there, just in a little bit of a shorter form. Let's erase this. Now we're going to talk about this magical constant, because this magical constant, it's literally magical, because it doesn't really give us any concrete answers to any of the questions we have, right? Because what did we say? We said that the rate of reaction depends on. We said that the rate of reaction depends on those 1, 2, 3, 4 things, right? Our equation here, we understand in a clear way only how this equation accounts for the fact that things react by colliding and the fact that concentration matters, right? 2 and 3, geometry and temperature, are dealt with by this constant K. But we don't really know anything about this constant K as of the moment, other than the fact that you can like kind of get it from experiment and like low-key just figure it out experimentally. But if you figure it out experimentally, as I said, this constant would then be different for every reaction at every different temperature, and that's kind of useless. That means like if you want to be able to accurately predict your reaction, that means you have to, each time you do it at a different temperature and a different reaction, you have to compute, like do a separate expensive experiment to figure it out. And that's kind of terrible, because that's a lot of money. We don't have that kind of money. We're high school students, all of us. Right? So we can't do that. So there is an answer to what this constant in fact is, and this is called the Arrhenius equation. And we will not derive this like we derived that because it's complicated and I don't know it. But I can give you, intuitively explain to you why it maybe is kind of like that. And the Arrhenius equation is the following. The fact that this constant here is equal to some other constant A times e to the negative EA divided by RT. E is Euler's number, the 2.7. And I'm about to explain what the other ones are.
Negative E of A.
Negative E subscript A.
Okay.
Euler's number to the power of negative E subscript A divided by R times T. Okay.
Wait, can you just like print this guy's name, please?
Arrhenius, A-R-R-H-E-N-I-U-S.
Oh, thank you. I never learned cursive.
That's on video now. You best hope people don't figure out your voice. Okay. Wait, so I've been writing all of this and you're like...
No, I've been able to read like most of
Okay,
it.
don't worry about it. So what's A? Actually, let's forget about what A is. We'll think about that later because that's the one that is least understandable. E subscript A, that is the activation energy. That is the activation energy. That's how much extra energy you need to add to like actually make the reaction happen. Okay. R, I think you've seen R, that's the like universal gas constant. Gas constant. T is the temperature. And it has to be in Kelvin. In Kelvin. Why does it have to be in Kelvin? Well, it's related to the whole reason of how we define temperature. If you remember, we said that temperature is if you have an object, the temperature of that object is the average kinetic energy of each and single particle. And then it's like scaled by some factors to get temperature. But that's like the whole core concept of it, right? And when you have temperature in Celsius, 0 Celsius doesn't imply that you have zero energy, as in the particles are perfectly stationary, right? So in that case, for almost everything that has to do with energy and relating energy to temperature, it doesn't make to use anything other than Kelvin or any scale where 0 isn't absolute 0. Does that make sense? Right? Because it just physically, it's not representing physically what it's supposed to represent. Celsius and Fahrenheit are just convenient for people because 0 is like tangible to us in those scales. Okay, that's great. Temperature in Kelvin. Now this mysterious constant A. This mysterious constant A is still mysterious. This is the constant that fixes the geometry of the reaction problem. It's just responsible for the geometry of the reaction.
Wait, sorry. So you're using like two other constants to find this K constant.
Yes. I'll explain why that makes sense in a second. Responsible for geometry of reaction. I'll explain to you why this is actually a vast improvement over that in a second. First of all, R is it's a constant that's always constant. That's like the universal gas constant. We know it. This doesn't change. This is just a known number. So that's easy. Now temperature is super easy to measure, right? So that's good. Activation energy is not that easy to measure, but if you have a fixed reaction, it always has the same activation energy, right? And then A is responsible for geometry. That's also unique to each reaction, but this doesn't change with temperature either. So what do we get? We now have to, instead of just finding K, now we need to find out what A is and what EA is, right? Because temperature we can easily measure, that's not a problem. So on one hand, now we have to figure out like two different things from an experiment. However, once you figured out the activation energy and this A constant for a single reaction, now you can compute this K for any temperature at all. And that's infinitely better, because before you had to calculate this not only for, not calculate, but experimentally determine this constant, not only for each and single type of reaction, but also for every single temperature. Now you can just if you've managed to figure out this constant and this constant, then you can do it for any temperature. You can just compute it, and you don't have to set up an experiment. So this is already amazing. On one hand, we have to find two separate things, but we have to find them once and never again.
Okay.
And this is already way better. And so now, what does our rate law look like? Now our very general rate law looks like R is equal to what? A times e to the negative activation energy divided by the gas constant times the temperature, and then times all of these like reactions to their respective powers, an, cn. Okay, so now we have a pretty comprehensive understanding of how rate works, of how fast the concentration of reactants changes in a reaction. We have a pretty good formula. Because this, if you look at this now, this accounts for all of these 1, 2, 3, 4 things, right? We have concentration left over from this part. This part explains concentration, right? Then we now have temperature, which accounts for temperature, and activation energy accounts for the fact that you need particles to have sufficient energy to actually successfully collide. That's great. And then we have A. A is responsible for the geometry of the reaction. That doesn't tell us much, but hey, at least we kind of now have a better understanding of what the relationships are between temperature and rate of reaction. Okay, so that's great. Let me get us some water. Now, we have more questions that we can now answer using this information. Actually, sorry, I had a thought, and I forgot this thing. Right. Before we start answering these questions, actually, before I even wanted to do this, I forgot to do one tiny thing. Is deal with the units of K, because K has really weird units. We're gonna have a look at that in a second. Okay, yeah, we've done with that. Is this good to erase? I think it should be. We've talked about that for like 1 hour. So it should be straightforward. Should have brought my cloth. My cloth is a little bit better. Okay. What did I want to say? Right, sorry. So I jumped a little bit with the Arrhenius constant because I wanted to do something else first. Let's look at this. Sorry, let's look at this equation one more time, where we just have the K constant and not like the actual formula for it. Sorry, because there was something else I wanted to look at. Let's look at the units. What are the units of K? Because we know that things have units like moles per decimeter and so on and so forth, right? Yes? Okay. So let's figure out what the units for R are. R is the rate of change of concentration, right? Do people agree?
Yes.
So R is concentration over time. People agree with that, yes? What units does concentration have? Time, let's say seconds. What does concentration have? It has moles per liter, right? And then actually, instead of seconds, I'm still going to write time because T is easier to write than seconds. Okay. These are the units on this side, right? Everyone agrees with this. Okay. Now let's look at this other side of the equation. We would expect that the units on the left-hand side of the equation and on the right-hand side of the equation should be the same units, right? Because like you can't have kilograms equal to liters because that doesn't make sense. So you'd expect this to be moles per liter per time, and this also to be moles per liter per time. So okay, we then get that this is equal to some units of K. In this case, when I'm writing K, I'm not talking about the constant itself, I'm talking about the units that K has. Times, what are the units of concentration? Moles per liter. So times moles per liter to the power of C1 times moles per, and then ... times moles per liter to the power of Cn. Do you agree? Someone's there doing renovations and stuff. Does this make sense to you? Yes?
Oh my goodness.
Yes? Okay, good. Now we can rewrite this as moles per liter. So this is equal to the units of K. This is equal to the units of K of moles per liter to the power of Cn plus everything up to Cn. People understand how multiplying and then adding powers works, yes?
This is why not to review order law?
Review the, no, this isn't the difficult nut yet.
Oh.
Not yet.
This is like exponents. When you multiply things, you add their exponents, right? Because this is all mole per liter, so we just add their exponents, right? So then, if we want to find the units of K, we can just divide both sides by moles per liter to the power of this power and get the units for K. Do you agree? Yes? Yes? Okay. I know people are tired after getting food, but okay, so we have moles per liter.
I'm distracted by this.
Moles per liter divided by time, so it's here like this, and then we're going to multiply by liters per mole to the power of this power. Instead of doing like 1 over, I just 1 over it inside. Like instead of dividing everything, I divided it on the inside. Yes? People understand that? Okay. And so we get that if we know exactly what C1 and Cn are, we can explicitly get what the units for K are. It's something like moles, like it's most likely going to be something liters per mole and then divided by T. Or maybe not, maybe this is like 1 and then it's just 1 over here. And then if this sum is 1 and you have only one reactant, then it's just 1 over T and you're good. Right? Does that make sense? We can now find the units of K in this way. If we know what C1 to Cn are. Okay, that's great. Now, for this, we therefore get that the particles that all collide at once determine the units for K, right? Because all of these particles collide at once. We get that the particles that collide at once determine the units for K, right? And in this case, we're going to introduce two definitions. I don't remember two terms. I don't remember what exactly they're going to be called in your course. I'm going to call them one thing. Your teachers might call it another thing because they actually know what they're talking about. I don't. I just kind of vaguely remember this from like a year ago. So I think it's called like order of reaction or something. So we're going to define the order of a single reactant. So wait, that's not how you spell order. Order of reactant.
Wait. I forgot. What are the C's again?
You have this reaction where you have C1. You have C1. C1 is a number. So you have A1, the particle A1. It's a type of particle. And then C1 of those like molecules or whatever they are collide with C2 of this type of thing.
Depends on whatever.
Yes. And that's why they're to the power of, remember, because we're looking at the total number of combinations.
So it could be moles, it could be molecules, etc.
What do you mean? No, this is always in moles. Oh, the C1? The C1 is a number. The C1 is just a number. It doesn't have units.
Oh.
Because it's the number of particles that collide. It's you're counting something, and that doesn't have. Oh, you mean in that sense? You never have particles collide in like. You never have more than like 5 things like or 4 even things collide at once. We'll talk about that later. But if you remember any chemical like equation that you've had, you've never had like 10,000. Right? You don't need moles. You can just count in ones. It's slow enough.
Okay.
Yes. So this like doesn't have units. Quote unquote. Okay. Order of reactant AI is going to be this number Ci. So that's this power here in the rate law. We're going to call this number the order of this reactant. Does that make sense? We're just giving it a name, nothing new. And then the order of the entire reaction, is this sum, C1 plus ... Cn. Note that the order of reaction, I'm talking about the CIs in the rate law specifically, not these here, and that's going to be important later. These are technically the same numbers, but we'll get that there's a small distinction. Okay, order of the reaction is the sum of all of these, all of these powers, and then the order of a single reactant is the one that's associated to the specific reactant. Does that bit make sense? Yes, no? I'm just calling stuff. I'm giving stuff names.
Oh.
There's nothing. Nods, not nods. Does it make sense what I called what?
Can you say it again?
Okay. We're now going to call this number the order of reactant A1. That's what this, if I say order of reactant A1, you're going to say C1. If I said order of reactant A2, I'd say you'd say C2. I'm just giving this number a different name. That's all I did. And then I said that the sum of all of these numbers, we're going to call that the order of reaction. I think that's what it's called. I'm going to call it. Maybe like it's actually called something different and I'm setting you up for failure because you're going to be confused, but oh, it's just a name. I'm not doing anything fancy. Should have mentioned that before I went to the Arrhenius constant because this is jumping.
The order of reaction is the sum of all the
Of all of those C's.
It's the sum of the reactions.
It's the sum of these of the number of how much of each reactant you have. Actually, don't think of it that way. Think of it as the sum of the powers that you put the reactants to in the rate law. The sum of these powers. Does that make sense? It's not a difficult thing. Yes, no? I'm just giving something a name. All right, and now we know that the order of reaction completely determines what the units for K are, right? Because the order of reaction is this number. Once we know the order of the reaction, we can figure out the units for K. Because that's the only thing here we don't know. But if we do know this, then we know the units for K. All right? Yes? Good.
Yes. Wait, that has units.
Pardon?
The order of reactions units.
Order of reaction does not have units. It has units of 1. It doesn't really have units.
Oh,
I'm saying that if we knew this number as a physical number, if you know the order of reaction, then you get the units for K. So the order of reaction determines the units for K. The order of a single reactant contributes to the units of K. But if you know the order of only one reactant, that's not enough for you to figure out the order of reaction. If you know some of these powers, that's not enough for you to find out the entire sum of all of these powers. Okay. This hopefully makes sense. Now let's go back to our original question, right? We wanted to figure out how fast the reaction is going. And we've successfully done that, right? However, this formula doesn't really account for the fact that there exists time. We know how fast a reaction is happening if you just take a probe, figure out the concentration of each thing at a certain moment. But we don't have like a graph of concentration over time, right? That would be a really cool thing to have. Come up with a graph for concentration over time. Okay, well, let's do that. Now, unfortunately, that's a little bit complicated. Unless you have a computer, then everything's easy. You can numerically solve most things. So we're going to restrict ourselves to a very simple type of reaction. In fact, we're going to restrict ourselves to 3 reactions. Can I still want that. Is it fine if I erase this? Am I going to be no, I'm going to be referring to that later. I'm going to use this board then. This board, what is this board? Yes, this board we can erase, because this board is no longer relevant. We changed our notation. We forgot about everything that ever happened. That's recording, right? Okay. Yeah, I'm still very sleepy. Well, you still have to listen to this. You know what? Maybe we should just not have lunch next time at all. Easy.
Yeah.
Or you guys show up at 8 a.m.
Oh my god. No, what actually it's I don't like that.
Coffee for lunch.
Coffee for that's no. Coffee is not good for you, so let's not do that. I can't allow that.
You said there's a second cup.
There's a second cup, so you get hot chocolate and
For lunch.
hot chocolate for lunch and the pastries and whatever. Okay, anyways, what was I saying? Right, so we're going to consider the following very simple reaction where yes, okay. we're going to consider the following reaction. Where you have A, it's just sitting, pardon?
Are we still on the topic of
It is going to, the units of K are kind of an aside to introduce these terms. To introduce, like, to motivate why we need the order of reaction. But this is actually a common question IB might ask you. They might do something like, we'll do a question like this later. They'll say like, oh, using this data, figure out what the order of each of the reactants in the thing in the equation are, using some data that they'll give you. Then you can find out the order of reaction, and then then they ask you what are the units for K. And then they might even ask you to like compute K given the data that they do. But we'll solve that type of question in a second. It's not difficult. It's very easy once you understand all of this. Okay. So we have this Arrhenius thing. And this is going to be very useful. So what are we going to do? Consider the following reaction. We're going to do this for only simple reactions. Remember, right now our question is, can we find a function which is going to tell us the concentration of a reactant after t time, right? We already have an equation that lets us find the rate of reaction, how fast concentration is changing, but we want to go back. We want to go from the derivative to the original function, which is how much concentration we have at a certain point in time. Does that make sense? Yes? Good, okay. So we can do this only with simple reactions. So we're gonna consider the following simple reaction. A is just sitting there, and then it spontaneously just falls apart into like, I don't know, something like D plus E. I don't know, it's just sitting there, it's not doing anything, it falls apart. So, this is a reaction where there is, what are the total possible, there aren't really collisions, but there's in a single liter, there's a total possible there's concentration of A particles that could do this, right? Yes? So we're going to multiply it by our constant, which tells us how much of those actually do fall apart like this per second. And then we're going to remember that now our constant is, we're going to remember that our constant is that, but to not have to write that monstrosity out each time, we're going to keep it for K as K for now, and then we're going to like figure it out later. Okay? And then we get that the rate is equal to this. Now, I think all of us can agree that the concentration is in fact a function of time. Because concentration as the reaction goes on changes with time, right? So I'm gonna write it in the following way. What's a cool letter, like for functions? That's not F. F is like
G.
Right.
R.
Q.
S.
No, we already have R. Actually, S is a good one. So let S of t be the concentration of A at some time t. Like it's a function. It's a function that tells us the concentration of S at time t. Do people agree with that? And I will now use S of t for like all of the following examples we're going to do.
Wait, I'm so sorry, but you know the equation R equals KA over here?
This.
No,
No, this.
this one. The one you wrote just above this one.
Yes.
Where do we get this from? I kind of.
This is the exact same thing as this.
Oh.
The only difference is, here I said like in a general way, if we had A and N possible reactants, right? Here, we have only one reactant. And there's only one particle is needed to explode.
I understand.
So everything else is zero. So, okay, that's the thing. I should stop pointing like this. I don't like it when people like poke their finger at it. I prefer knuckles, but then I sometimes poke a finger at it and then I get pissed at myself. Okay. Am I allowed to say that in front of high schools? Probably not. Okay. Concentration of A at some time t. So let's look at this. So now let's rewrite this equation, because this equation tells us the rate at a specific fixed point in time when the concentration is exactly a certain concentration, right? So let's add time to this. What was so we have R is equal to K times S of t. Do you agree? Now what was R? R was the rate of change of concentration. Do you agree? And the rate of change of concentration, wait, do I have, wait, I've been talking for 30 minutes already? No way.
That's pretty funny.
I'm very slow, okay. Let's hope this takes 1.5 to 2 hours. We said that R is the change in concentration per unit time, right? And we said that that's the derivative of the graph of concentration. So we can say that this is the derivative of S. Do you agree? So you have derivative is equals to k times the function itself. This is the part where we enter the actual math part, which is never really discussed in your chemistry courses. They just give you the following results that we're about to derive and just tell them, well, this is true, and memorize it. But I think it's not too difficult with the calculus that you already know to figure out how to, like, to give an explanation to the stuff you otherwise learn. Okay. Now, this is called a differential equation. Because what is this? You have the function itself, which you only know how to relate the derivative of the function to the function, right? So you don't actually, but using this equation, you can still figure out what the function is my point. How are we going to do this? Well, we know integration, so we're going to try and integrate. And you can't, like, there's many kinds of differential equations. Not all of them are easy to solve. Most of them, I think, like, don't have a solution, which is why, or at least like an easy analytic solution, which is why I'm restricting ourselves to like very simple reactions, which is A and it does something, it falls apart into two. That's why I'm using simpler, because otherwise this would be very difficult to solve. Okay, now watch this magic. I'm going to take and divide both sides by S of t. All right?
Okay.
Equals to k. All right? Now I want to integrate this with respect to t from both sides. How do people think we should do that? If we integrate both sides, what do you think we would get on this side? Look at this very carefully. What is the integral of this with respect to time? If people remember anything from their integration. S of t dt equals to integral of k dt. Okay, so at least tell me what the integral of k to time is. That should be very easy. You have a constant and then you integrate it with respect to time.
Okay.
No.
Wait a second.
KT, there we go, okay. So we get that one of the sides is equal to KT.
Oh, my bad. I think I did French.
Okay, I'm gonna snake all the way here. Okay, so we have that this integral is equal to S prime of t divided by S of t dt. This is equal to KT. Now let's actually compute this integral so we get our full equation. You know what? I'm going to do like a small aside next to the aside, like the math detour portion, just so that you guys get a little bit of a reminder of how all of this works. Okay, as you guys remember, if you have a function f of x, and inside of it you have a function g of x, so you're taking f of g of x. Do you agree?
Yes.
If you take the derivative of this, this is equal to the derivative of g of x times the derivative of f evaluated at g of x. People remember this, right?
Yeah.
So if you were to take an integral of this, you would get the stuff inside, right? Yes? Now, let's replace this with a concrete example. Suppose you had the ln of f of x, right? What is using this formula, we get the derivative of ln of f of x. What is the derivative of ln? Do people remember? The derivative of ln is 1 over x. So d over dx of ln x is equal to 1 over x. This is something you should remember really well. So if we take the derivative of like this entire thing, then we get what? The derivative of the stuff, of the thing inside. So we get f prime of x divided by the derivative of the thing outside, the derivative of ln, evaluated of f of x. The derivative of ln is 1 over x. We evaluated it at f of x, so we get 1 over f of x. Do people understand how we got from here to here? Like I need everyone to be on board with this.
Okay.
No, like actually, if you have questions,
I just need a moment.
okay, take a moment. That's fine. You take the derivative of the thing inside and multiply it by the derivative of the thing outside, which you evaluate the derivative of the thing outside at like what the value of g of x is. So if you took ln, the derivative of ln is 1 over x. But we want to evaluate the derivative of ln at what is inside. So the derivative of ln is 1 over x, but we want to evaluate it at f of x. So we plug in f of x instead of x here.
Oh, okay.
Right? So we get f of x, and then we have the derivative of the thing inside is just the derivative of f of x. Right? So we get f prime of x divided by f of x. Is the derivative of ln of f of x. Do people agree with that? Yes? Okay, now, if you look at this, doesn't this and this look very similar? Incredibly similar.
Wow.
So can someone tell me what the integral of this is now? Yes, it's ln of s of t, ln of s of t, like this, for bracketing. We're going to add equals to kt, and then we're going to add like a plus c, because why not? Okay, does this make sense? So now, using this, we now have to come up with a function for s of, solve for s of t. Right? You remember that ln is a number such that if you put ln of x is a number such that if you put e to the ln of x, you get x back, right? So if we put e to the power of both of these sides, you get whatever is inside, right? So you put e to the power of ln of s of t, you get s of t. Do you agree? Ln of s of t, this should be equal to s of t. Do people agree? Do people agree with this statement?
Yeah.
Okay. And then e to the power of kt plus c is just e to the power of kt plus c. Yeah? Now, so we get that s of t is equal to e to the power of kt plus c. Actually, wait, I think there might be a negative somewhere that I'm missing. Is there? I don't think there is here. I don't think there is here. And actually, this is I think this would be the function for how much products you're making, not for how much reactants you're using. If you're looking at how much reactants you're using, you just put a negative in front of here. And you'd just be looking at, like, instead of adding things, you're like subtracting. Does that make sense? I think that's how it would go. So now, this is great. Now we have a very explicit equation for how much products I'm making at a certain point in time. Do you agree? Actually, wait, no, there does have to be a negative somewhere here.
Wait, the rate formula that we were using before, that's all like the product that you're making?
R is the rate of change of concentration.
So it's only,
R is the rate of change of concentration of one of the products you're making.
and you said if we were doing reactants, we would have to subtract?
If you did what?
Which one are we subtracting? Like you said,
No, you just put a negative in front of here, like the entire thing, because it's all multiplied. I think you just put a negative because now you're losing products. Right. Let me think about this. Does this answer make sense? Is this the answer that I wanted to get? Hold up, I'm not sure. Sorry, I'm setting up. Is this right? Hold up, the graph, wait, I'm gonna actually pause this because this might take me a while to figure out. Okay, for people on video, the initial equation where we have R equals K times concentration of A, there should be a negative, R is equal to negative K concentration of A, where R is the rate of change of the concentration of A, because A is the reactant. So we should be losing the reactant. So we should we should be losing reactant. So how much reactant we are there should be a negative rate of change. Slope should be downwards so that we're actually losing the reactant
So does
and
this
getting
apply
less of it.
to all the formulas we're discussing?
This applies to only this, what I've discussed here. So if there's a negative here, there's now a negative here. Okay? Now there's a negative here. You just have to add in a bunch of negatives. Now there's a negative here. Now it's negative kT. It's negative kT plus C, and it's e to the power of negative kT plus C. So S of t is equal to e to the power of negative kT plus C.
So in this case, for R, we're solving for...
R is the rate of change of A. And if R is the rate of change of A, then it should be negative, because you should be getting less of R over time. Because if R was positive, that means you have a positive slope. That means you're gaining more slope. You should be losing reactance, so it should be negative. You don't have the negative if you have if this is the rate of reaction of the products. And you have to understand that the rate of reaction of products and reactants should be just plus minus, because if you used up these many reactants, at the same time you produce the same amount of products. Or maybe there might be like a factor of like 2 or 3 there or something. If you're like for 1 mole of one thing you produce 2 moles of something else, like maybe there might be a factor in that case. For this reaction, you need this negative here because you're using a reactant. Okay, sorry, I messed that up. Does that not the first time I messed that up? Does that confuse people, or are we okay? We figured out what the mistake here was and why that was a mistake. Okay, so we get this graph. What is so useful about this? Well, because why do we care about this? First of all, if you want to if you have a reaction like this and you wanted to figure out the K constant, right? It would be quite tedious to find like the rate of the instantaneous rate of reaction. Why? Because that means you're going to have to you're going to have to set up an experiment when you measure the concentration of A over time. Because once again, when you measure stuff, you don't measure stuff continuously. You measure like dots, right? And they're going to have to like subtract these 2 dots, divide by time, and to approximate the slope. But then that would be like a really weird, like a really weird, what's it called? Sorry. It would be like a weird relationship. Sorry, not weird relationship. This would have a lot of error and uncertainty. Because if this was a curve, then you can get exactly the slope. But if it's these points and you're like finding the secant of these 2 points, well, maybe the slope is like more like that, right? It's very difficult to get an accurate answer. However, if you look at this graph, how can we have values for S of t at different S's and T's. How can we figure out KT? Well, you have it right here. You see that if you plot the ln of this function, you're going to get a linear graph, right? And this linear graph, in fact, if you plot ln of S, so ln of concentration of A, remember, S is the concentration of A over time. This is going to give you a linear graph. And if you verify that if you have a bunch of points, then you can always draw a line of best fit. And lines of best fit are like pretty good. And we can do uncertainties with lines of best fit. If any of you have gone to like the thing I did last year for IAs, I talked about how to do uncertainties with lines of best fit using software. It's not that bad. And it's quite accurate, surprisingly. You get more or less low uncertainty if you don't mess up. I actually once on a lab got too low of an uncertainty and got marks because my uncertainty was too low. But it probably was too low. It probably messed something up. Because I calculated that in like 2 hours. Okay, ln of A, and this is 2 times. You can get that the slope is our constant K. Is our constant K that we wanted to find. So we now know that for a reaction with order 1, we now know how to find the constant K from experiment, right? And this is quite good. This is quite good. And actually, we still haven't really used the fact that it's all of these things, because I forgot something. But okay, We now know how to find K if we didn't know that it's that. But actually, now that we can find K, we can maybe try and find like all of these other things. Okay. Actually, if you found K at two different temperatures, right? If you found K at one temperature and K at another temperature, you have K1, K2, you'd be able to divide those two Ks by each other, right? This would cancel out because this is the same regardless of temperature. And then you'd be able to solve for activation energy if you measured the temperature for each one of them. So in fact, now we have a way for this kind of reaction, not only to calculate K, but if you manage to do the experiment at two different temperatures, you can also now solve for A and E of A. And that's great. So we've already solved this problem. Is this good? Can I erase this? Hopefully. Okay, hopefully I don't mess up the next thing. I think the next thing after I mess up the first thing, I do the next thing better. Okay. And guys, we're getting places eventually, I promise. And also, for those of you wondering, that the graph for this reaction, because it's e to the negative kt, it would look something like that. And it's going to be like an exponential graph. Well, I mean, you don't have much at negative time. You start off with this concentration. It's like an exponential graph down. And then it either limits out like at 0 or something else. Actually, wait. Does it limit out at? It should limit out at 0. Yes. It has to limit out at 0 because we have only one reactant involved. If we have only one reactant involved, that means the reaction has to go to completion because you only need one thing for it to react. So it will always limit out at 0 in this case. In this specific case. Yes. And we can see that from the equation because it's e to the power of negative kt plus c, but this plus c is the same thing as like multiplying by e to the c here. So you have just some other c prime times e to the negative kt, right? And e to the negative kt, if you take a very large t, this number is very small. Because it's like e to the negative kt is the same thing as some constant times 1 over e to the kt, right? And if you take a really large t, this number gets very small, right? So you know it's approaches 0 in the end, right? And that makes sense because you have only one reactant. That reactant has to go to completion. The reaction has to go to completion. If you have only one reactant, there is nothing that like limits the reaction. There is no limiting reactant, where like one thing is used up and the other is. Here you have to use up everything eventually, like at infinitely much time. Does that make sense? Why I'm saying that? Why is that relevant? Yes, that's a different c. Why? Because e to the power of kt plus c is the same thing as e to the power of c times e to the power of kt, right? But if c is just a constant, then e to the power of c is also just a constant. So I just kind of relabeled it as c again because I'm lazy, and so that you're more confused. But yes. That's actually how you would normally solve this equation. Normally this kind of differential equation you just solve by writing down the answer because it's so easy. And that's why people just write c times e to the power of negative whatever instead of doing like e to the c. Doesn't matter. Ask Dr. Dykstrom about differential equations. He'll tell you all about them.
Oh my goodness.
I mean that's where I first heard of them, and then that was my IA topic, my extended essay topic, my math IA and physics IA. Like it was what I did for the next like 2 years.
Goodness.
Yes. Probably, watch it's going to be what I'm going to do for the rest of my life. That'd be amazing. Actually, no, I don't know. Analysis or linear algebra, the forever question of first year. Okay, so now that we have this, let's consider a more complicated thing. You have 2 of A.
Wow.
And now these 2 particles of A collide with each other and make something else. Or maybe like they either make D and E, or like they make A2. It doesn't matter what they do. The key thing is that you need 2 particles of A to collide. You now have this completely new thing. What changes in this formula? One thing changes in this equation. you get a squared,
Oh my goodness.
right? And people remember why a squared, because we can make a times a possible pairs of possible collisions, right? Now once again, so this makes sense how we got here so far. This makes sense. It's the second time we're doing it, so it should be okay. All right, now let's do the following thing. Actually, I should get a sip of water. I'm gonna do the following thing after I take a sip. How much time have we been? Oh, right, because I restarted it.
I don't understand what the point of drawing the rather than doing the differential equation. So it's just to show us that.
The point of the differential equation is, here we have a rate law, right? That tells us the speed of how fast things are going. But that's not useful. It's useful, but it's not as useful. It's much better to be able to tell me after 10 seconds, I'm going to have exactly this much. That's like way more useful.
Oh, so we just created the equation for the rate.
This is the equation for the rate of change. By integrating when we solved the differential equation, we got an explicit equation for the concentration at a specific time. This gives us the rate of change of concentration. We got that the concentration of A at time t was equal to e to the negative kt, like this.
Okay.
Where this is some constant, actually this c, we can figure out what this c is quite easily. Why? We plug in t equal to 0, right? At t is equal to 0, so the concentration at 0, right, is going to be c times e to the 0. Do you agree? What's e to the 0? 1. So we rewrite this as 1. So the concentration at time 0 is this constant is the concentration at time 0. So we get that yes.
Oh, I didn't.
I plugged in, instead of t, I plugged in 0, right? At time 0 when our reaction is starting. And I get e to the 0, which is equal to c, because e to the 0 is 1. So you get that c, this constant in front of the thing, is the initial concentration at time 0. So now we have a very explicit equation that the concentration after time t is equal to the initial concentration times e to the negative rate constant times t. And now this is like great, because we can figure this one out from experiment very easily. We just have to measure the concentration at like different points in time, take the ln of that, get the line of best fit. That's easy to do, not by hand, but in principle. You will be asked to do it by hand on an exam. It's not that bad because they don't ask you to do uncertainties with your line of best fit. I don't think.
Thank God.
If they did, actually, I mean, even if you did uncertainties, it wouldn't be. Actually, it would be annoying.
It would be painful.
It'd be painful. Yes.
Okay.
See why this is now like a huge improvement over that. Yes? Because if we want to get that back, we just have to differentiate this. And that's easy. Everyone knows how to differentiate. Because everyone has access to the internet, and then you just Google the derivative and you're done.
Okay. So
You think people do it any other way in real life? No. You think someone computes derivatives by hand? We all have really good software that does it for us. Never again.
Never again.
Actually, not never again. Like, you still have to understand how, like, you still do need to do it
I
at times.
understand now. Oh my goodness.
Exactly. So we kind of went backwards from rate to the actual, yes.
How is C A?
Very easy. A naught is the initial concentration when the reaction just started, right? Do you agree that this is true? Now we plug 0. Let's plug 0 into this function. Let's see what's happening at time 0. We get e to the 0, which is 1, which is c. So the value of the function at 0 is equal to c. Very simple trick. And this is like called. This is the whole idea behind this, is that the rate of reaction tells you how fast the reaction is going, but it doesn't tell you where the reaction started off from. Because if you know how fast you're going at any point in time, you can figure out how far you have gone once you've started something. However, to be able to tell me exactly where you are, you need to know where you started from. And which is exactly what we needed to fill in that piece of information that's not present in here. If that makes any sense. And that's why this is better, because this has like one extra piece of information over that.
But I still don't get what this C is.
It's just a constant. When we integrated, we needed to write a
like
plus C because we just had a constant.
Okay.
And now we found out that this constant actually has physical significance. That it is in fact the initial concentration you have at time 0.
Okay.
And now this makes perfect
Oh,
sense.
okay, yeah.
You start off with your initial concentration and then you scale it down as time goes on.
Exponential.
Yes.
thingy. Yes. What?
Okay.
Like,
Now-
so these, like-
Okay, so now, see, this is what I showed you. Now, the thing that IB will ask you to just know, IB will just ask you to just know if you have a reaction of order reaction of 1, that the graph is like an exponential graph like this, and that if you take a ln of this graph, it's a straight line where the slope is k. That's what IB would just tell you. I told you why that happens. It's not just magical. It's a very easy, like you integrate one thing and then you already get this. Like what we did, I don't think was impossibly difficult for you guys to understand. However, it explains why for a first order reaction, I mean, it's no longer, I wrote something different. Why for a first order reaction, it's e to the negative kt graph and the ln is, the slope is k. Well, it's negative, the slope is negative k, but the absolute value of the slope is k. Okay. Yes, makes sense. Very nice. And you would be asked to like, given this graph, like not a continuous graph, but like some points on this graph, they tell you like find k, and they tell you this is a first order reaction. Find k, and you're gonna plug into your little silly calculator, calculate ln of each point, plot it on like a different thing, the points. They're gonna like arbitrarily draw a line of best fit, like completely willy-nilly, and then like count the squares to figure out the slope, because that's the best thing you have, and then you'll figure out what the k constant is for that reaction. Now, that's for this kind of reaction.
Oh, good.
This is once again, this is only for like when we have just A alone and it falls apart. Now let's look at a different case. This case might actually be easier because the integral for this is easier. We have 2A, right? Now we have a squared for the rate law. The rate law is equal, r is equal to negative k times a squared. Notice that now the units of k have changed, right? I need another system. This is like, oh wow. Am I either really slow at explaining things, or there's a lot of content, or both, or I'm just sleepy? I don't
We're
know.
gonna choose to believe that there's a lot of content.
Yes.
I mean,
Uh,
it take a semester to learn this stuff, so.
I mean, I'm not showing you exactly what you guys are going to be learning. I'm showing you half of the, like, why what you're learning is going to make sense, but like, there's a lot of practice problems which I'm just not showing you at all. But once you understand this, the practice problems, like, you'll understand the practice problems and they'll be easier, hopefully. Okay, once again, I'm going to do the whole thing where the concentration of A is equal to S of T. Or like, define S of T to be the concentration of A over time, right? Because writing like A of T is just weird notation. So we get the derivative of S of T is equal to negative K times S of T all squared. Do you agree? Last time, what was our trick? Last time we just divided both sides by S of T squared, right? Last time we divided both sides by whatever was here. That trick has worked so well last time. Let's do it again. But now we're going to also multiply with the negative. So we're going to have negative S prime of T divided by S of T all squared is equal to K. This negative moves here. People agree? Now, we're going to integrate both sides with respect to T. dt, integral dt. All right. Can anyone tell me what this integral looks like? Can anyone tell me what this integral looks like? This one should be easier than the previous one. So I'll give you a simpler one. What is the integral of 1 over x squared dx? Negative 1 over x squared. 1 over what?
Over
Okay, let's try this one. Suppose you're given x to the n. What's the derivative of x to the n?
n x to the power of n minus 1.
N times x to the power of n minus 1. Okay, so suppose you have x to the power of 2. 2. N, so the minus 1 is 2.
X to the power.
So
Negative 1.
1 over
x, exactly, this is 1 over x. And plus c.
Oh, yeah.
Yes, people understand? Because this is x to the power of negative 1, right? 1 over x is x to the power of negative 1.
One.
No.
No.
1 over x is 1 over x. So ln is different. The integral of, if you integrated this one other time, then you'd get ln, right? This is the derivative of ln. But this is the derivative of 1 over x is negative 1 over x squared. Because if you plugged in x to the negative 1, you get what? You get negative 1 times negative 1 minus 1 x to the negative 2, which is negative 1 times x to the negative 2, that's this, negative 1 over x squared. People agree with this. Now we get, hey, we have this derivative up top, but that's like because of how chain works. If you did if you did 1 over f of x and took the derivative of that, you'd get this. I mean, I'm not going to explain another time. If you took the derivative of 1 over s of t squared, 1 over s of t, you took the derivative of that, you'd get this. So the integral is, I'm going to, can I erase this part? Okay. Also, like the people who are shy in nodding, don't be shy in nodding, because the people who are like very eager to nod, they understand things, they nod, you get left out. So like, nod more if you're not nodding enough. Okay, there we go. In case you don't nod at all, that's fine. We'll like leave you up a little bit. So this is 1 over s of t. What's the integral of k dt? That is just kt, and we're going to add a plus c here because we don't know part. Now, how can we solve for s of t? We can solve for s of t quite easily. We can say that, hey, s of t, like just multiply both sides by s of t, divide both sides by kt plus c. We get that s of t is equal to 1 over kt plus c. Figure? So, now we get that for a reaction where you have two particles collide, and that's all that happens. Their concentration over time looks something like this. It's 1 over something, plus something. So it kind of looks like similar to the e to the negative graph, but it's different in some sense. First thing that we can notice is that let's once again find this c. Finding the c is quite useful, right? If we plug in t equals to 0, so f sub 0, we get 1 over c, right? So now the c is actually 1 over the initial concentration. Also remember that S is the concentration over time. Do people remember that? S is the concentration over time of reactant A? Yes? Are you nodding or are you just sitting there? Okay. S of t is the function that tells us the concentration of A at different times t. Yes, that we remember. So this is concentration of A. Now, and so we get C is equal to 1 over initial concentration of A at time 0. Okay. Yes? Okay, well, let's go get her.
Oh, okay.
I'll stop. Okay, so I'm now going to once again try and explain why we're doing all of this. Our entire goal from the very beginning was that we are like a chemical engineer somewhere in industry, and we have this factory that's producing this thing. And I want to tell my manager how long it's going to take us to produce like this much product, right? So I want an exact like graph of how much stuff I'm making to time. That makes sense. That's a useful question to ask. Now, since I'm asking that kind of question, ideally, we'd want to just directly be able to find a formula for the graph of like the concentration of our reactant to time. Because if we know how much reactant we've used up, then we can figure out how much product we've made from our chemical equation, right? Makes sense. However, getting this graph directly is quite complicated. So we said, hey, how about I make an equation for something simpler like rate, and we made an equation for something simpler like rate. And in fact, we didn't even bother figuring out what all of these like how temperature affects it, how whatever affects it. We just put a constant in it and just said it works. And okay, that's very simpler because we just said it works and like wrote some things and just claimed that it works. And that's very easy. And now that we have this equation, we still want to answer the original question of, well, how much stuff do I have after time t? Now that we have the equation for the rate, we go back to solving the more complicated problem, but now this helps us solve that problem in an easier way, because now we can just integrate, and that's a calculus question. And calculus questions like of this type are easy to solve. Maybe like this was easy to solve because we could find the function explicitly. If there were like other reactants and so on and so forth, you'd be able to like the computer would be able to solve it for the most part, quite easily. And then the whole point was, now, okay, we introduced this magical k constant. How can we figure it out from experiment? And how we can figure it out from experiment is the next question. So that way we can predict things for any possible initial concentration, right? That's the whole point. And now, by integrating and figuring out what the exact functions are for the concentration to time, once we do that, then for example, for the case where we just had A falls apart on its own, order of reaction 1, we found out that the graph of the graph is something to the power of e to the negative kt. And we noticed, hey, if we take ln of all of our concentrations, we just get a linear graph to time, right? And then that's very easy to find k from that. So we've kind of did something simpler, used that simpler thing to solve a more complicated problem. And then now we have a way to find this magical thing that we came up with to fix all of our issues from experiment in a relatively easy way. And another thing is, measuring concentration versus rate of change of concentration, you can't really measure rate of change of concentration directly from experiment. You will always end up measuring concentration first and then trying to somehow calculate the rate of change from it. But as soon as you try going from in experimental data from concentration to rate of concentration, because the data you collect, it's not like a continuous line, it's points. You're gonna be calculating the derivative between these 2 points, finding the slope of the line, but that's inaccurate. Because this line, maybe this line's like this, maybe it's like this, maybe it's a little bit like that. Because you don't have enough information about it. So this is always gonna, trying to go to this equation directly from this data is going to give you a lot of uncertainty. But here we've come up with a way where we don't need to actually manipulate this data in a complex way to just directly get k. We just take ln of everything and then it's easy, right? Now, for the, okay, so this is something that's you aren't supposed to instantly understand. It's something that you will understand over time the more you think about it.
It's so complicated.
Pardon?
It's so complicated.
It's not. You're gonna think about it for a little bit, and it's gonna be very easy. But once again, that's why IB doesn't require you to know this. They just require you to know that the slope of, if you have order 1 reaction, if you take ln of the concentration, you get that the slope is k. That's all they require you to do that. But I found that confusing because I didn't get why that's the case. Now it's clear why that's the case. Very clear.
You're less confused or more confused.
Okay, that's a question you'll ask later. Okay, don't worry, we're almost done with this. The last example is going to be very easy. So we have SFT is equal to 1 over KT plus C. So we have the concentration at time t of A is equal to this equation, right? Now, if we are given some points of what the concentration of A is at different times, right? To find K, it would be very convenient to plot 1 over a. Do you agree? And 1 over a is 1 over this, that's just kt plus c. You're going to get a linear function like this, kt plus c, where the slope is, once again, the k constant, the magical k constant we've always wanted to find. And now, once we know the magical k constant, now we can always come up with we can now always come up with this function regardless of what our initial concentration is. And we can always tell our boss that after 5 hours you're going to have 1 gram of this very expensive thing, or I don't know, in your factory. And that's the whole point. Okay, so now we know that for reactions of order 2, to find the constant K, you do 1 over the concentration. Not ln, you do 1 over the concentration. Okay, that's like the takeaway IB wants you to take from it. Okay. Do we at least understand that for order 2 reaction, 1 over gives you Kt plus C, and for a 1 order reaction, ln of that gives you negative Kt plus C. Yes?
Mm-hmm.
And C's in this case are like different things. Yes? This makes sense? We're good. Once again, like you will come back, you'll think about this a little bit more, and then it becomes very, very easy. I thought about it for a semester, and then it became very, very easy.
We have the head start. We have the head start.
Yeah, you have a huge head start over me. Over me, I said. Okay, I maybe shouldn't have already said, but that's fine. Now we're going to look at the very last one, where we have none of A do anything and then something happens. Don't ask me, it's going to make sense how that works in a second. But there is no A involved, and then things just happen. So we,
So cool.
yeah, so like A gets used up, but it doesn't do anything. This is magic. We already have a magical constant, now we have a magical reaction. We have an A, which doesn't do anything, but it gets used up in the reaction. I'll answer that question after I solve this first. I just want to solve the differential equations first, and then it's going to make sense. It's going to make a lot of sense. At least the part where, okay, so you have something, and then you get something else. And then A is used up in the process. So the rate law for that is just K. Do you agree?
Yeah.
And in this case, the rate law for that is just K. Because you don't have any A's at all, so it's A to the 0, which is 1.
Wait, but you said there's A's being used up in the process.
A's are being used up, but they're not colliding. They're just being used up. They're not colliding. They're being used
They're
up.
not part of the product.
They're not part of the process of the reaction.
Are they part of the product though?
No. They're being used up to make the product,
Yeah,
but they're not like
in the product.
they're not in the product.
Okay.
They're reactants which get used up, but they're not part of the reaction.
Okay.
Like, think about it this way. They don't. No, not a catalyst. They don't contribute to the rate of reaction. They don't contribute. They're still reactants, and they get used up. They just don't contribute to the rate of reaction. And I'm going to explain how that's possible in just a second. Just hold that thought. And in this case, R is just K, because A is, none of them are colliding. So we get that the concentration of A, the rate of concentration of A, is equal to K, right? This is very easy to integrate. You get that the concentration of A is equal to KT plus C.
But that's a derivative, right?
Pardon? That's a derivative.
Okay,
Apostrophes are used for derivatives.
No, I thought it was
Because,
1.
yeah, no, because ddx is too difficult for me. It's too much writing. I don't understand it. I get tired writing all these. I'm already sleepy. So. And hey, this is already a linear graph. You don't even have to do ln out of anything. You don't have to whatever. You just like, and then slope, and you're done.
This is crazy.
Okay, and then this one's easy.
Wait, so it's A by T, right? And then the slope is K.
Okay.
This is so fun. I love it.
I know it is very fun. It's also very easy. Okay. Have people copy this down? Can I just straight up erase this?
This is the worst one.
3 lines. I'll add in integral sign too, just for you. So it makes more sense how we got from this step to this step.
Very helpful.
Okay. Can I erase this?
Yes.
Okay. Now let's figure out how we can have something that gets used up but doesn't actually do anything. Because that doesn't make sense. Well, let's go back to like how we derived this formula. In this formula, how did we derive it? Our whole point was that we have all of these A1, A2, and whatever, and they all collide at once, right? And that's why we look at all the possible collisions that could happen with these, right? They all collide at once and they all successfully react. Now, if I give you 10 erasers or 10 pieces of chalk, actually no, 1, 2, 3, 5 of you, I'm going to give you 6 of you, I'm going to give each one of you a piece of chalk. And then I'm going to tell you, throw these pieces of chalk such that they all collide mid-air together at the same time at the same point. How long is it going to take you guys to successfully do that? Maybe you'll get lucky. Probably not. Which is why something like this is incredibly unrealistic, where you have like more than, it's highly unlikely that you'll have like more than 3 things collide, ever. That's the first one. You will never have more than 3 things collide at once. That's like already incredibly rare. 2 things colliding at once, easy. 1 thing just exploding, easy. But more than that, like that just doesn't happen. Right? So at any point in time, really your order of reaction is always going to be like 0, 1, or 2. Never more. However, we then have the following question. You've definitely seen reactions where you have more than 3 reactants. So what happens there? Right? If we say that no more than like 2 or 3 things can collide at once, what happens to all those reactions you've seen where you have like multiple reactants? Well, the obvious answer is they don't all collide at once. They collide in steps. And this is where we get the idea of a reaction mechanism. A reaction mechanism. I'm going to give you a vague example to kind of maybe give you some intuition. Suppose you have A plus 2B plus C turns into A, B2, C, right? This is what? This is 4 things have to collide in space. Not only do they have to collide in space, they have to collide strong enough such that all 4 of those things stay clumped together. That is like incredibly impossible. Like, can you throw 4 chalks so that they all collide and all stick to each other?
Yeah.
No, you can't. So we definitely know that like most likely what happens is 2 things collide, stick together, and then another 2 things collide, stick together, and then a third, like then they combine together. So there's multiple possible reaction mechanisms for this. And I'm going to give you like a potential reaction mechanism for this. Suppose the first thing that happens is A plus B turns into an AB. All right? Suppose this happens. Then the next thing happens, we take this AB plus another B. This turns into an AB2. And then suppose we have the third step, which is AB2 plus C turns into A B2C. And now this makes sense because at any point in time now we only have 2 things colliding. And this looks realistic. Right? However, all of a sudden, we can't really use this formula. Why can we not use this formula? Because this formula only talks about stuff that collides at once. Yes. This, now we already get that all of these things don't collide at once. So we can't just say that, oh, the rate law for this is equal to like K times A times B squared times C, because the assumption of this formula is that all these things collide at once. These things do not collide at once. Why is this relevant? Because each one of these reactions, one of these substeps, could have a completely different activation energy. Each one of these substeps could have a completely different Arrhenius constant as well, and like all of these things. So all of some of these steps could be faster than others, is what I'm saying. Right? So we can't just use that rate law for this case. But it would be nice if we could come up with a rate law for them. And we will next time when we talk about equilibrium, because that's going to be useful. But the whole point is, suppose that this step is very easy. A and B colliding and sticking together is a very easy thing to do. They do it all the time. So this is a fast step, right? So A plus B, making AB happens very quickly. But then suppose AB plus B has a really high activation energy for this to stick together. And this step happens excruciatingly slow. So it's the slow step. And then this step also happens like fast. I don't know. C reacts easily for whatever reason, and it's like sticking to AB. So, in this case, I'm going to ask, does A contribute to how fast the reaction goes? I guess so, yes, because you use A to make AB, and then you need AB in the slow step, so that's useful. Does B contribute to how the reaction goes? Yeah, because you have B here, you have B here. Does C contribute to how fast the reaction goes? Well, not really, because this is the slow step. This happens really fast, and then this happens very slowly, and then this happens really quickly again. So the rate of the overall reaction is limited by the second step, not the third step. Because this is the one that takes a lot of time. While this one, like, you guys have a really good activity, I think, that you normally do, where you, like, I think it's for, like, this cutting activity, where you are making some kind of decoration. This is what I think one of your teachers will make you do in class. We didn't do it because we were COVID kids and we missed out. But hey, we didn't write any exams, so I guess that's a perfectly fine trade-off, not to do some cutting. The idea is something like this. You have like a station of 3 people. One person like draws something, the other person cuts it out, and the third person like just folds it or something, right? And actually, not folds it, the third person say like colors it in crayon, right? And it's like they don't have to do much coloring, they just like 5 seconds. The person cutting has the slowest job, right? So how fast you guys are making these decorations, you have a person drawing, a person cutting, and a person coloring. It doesn't like, you can, the last person who is coloring, you can color a little bit slower, because the person who's cutting is still not done making like the next thing.
Oh, you're doing it simultaneously.
Yeah, you're doing it all simultaneously, right? But then all of these things are happening simultaneously. But this person's taking so slow that this guy has already used up all of the AB2s, and he's just waiting for this guy to make more, right? Which is why this is all of a sudden the rate it's called the rate determining step. Rate determining step. Rate determining step. And now what do we get? We get that C participates in the reaction. It does collide with things. It does react quite successfully. It gets used up to make things. However, it doesn't actually affect the rate of reaction because it happens after the slow step. And that's how we could have like our rate law that we just solved for, where C is not even in the, like A was not in the rate law at all. In this case it would be C. But C was not in the rate law at all. And you got a really simple graph for that. And that's how these things happen. How much time do I have? I have lots of time. Infinite amount of time. Okay. Does this make sense now?
Yes.
Okay. And how like the previous thing also makes sense?
I get
Now this whole thing.
Yes.
Okay, there we go.
So it doesn't matter.
Yes. So now once again, it would be really nice to be able to get a rate law kind of like this for this. It is possible, but we'll do that when we get to equilibrium, and that's a little bit more complicated. That's not even actually something you are required to be able to do in IB, but I'll show it to you because it's fun. However, what I will tell you, I will definitely tell you this, is that the rate law does still have this same form. It's just that these coefficients are like, it's still some constant times some like concentrations to some powers. And the concentrations are still the concentrations of A, B, or C, depending on which one of them is actually relevant or not. But these powers, you can no longer read them off from here. You need the mechanism, and you need to know which thing is the slowest and which things are fast. Now, the next thing, you can almost never guess the mechanism just by looking at the reaction. It's very like, you can't just know the mechanism, you can't just predict it. Most of the time you have to figure it out from experiment. Or you have like some mega galaxy knowledge in chemistry that you can sometimes figure it out, but very rare. So we're going to solve, I think, now that I've introduced this, I'm going to solve one sample problem, and then we will be done. Okay? And in general, if you remember the sample problems that I mentioned, you could be asked to do something like this, where if you remember at the very beginning, you're given like a graph of the concentration of something to time, like in a normal case, and be like, oh, what if we like increase the concentration? How would the new graph look relative to the old graph? And this is a type of question you might be asked. A type of question you might be asked is like what we were just talking before. You might be given some points of concentration of A to time. You will be told that, okay, A is a second order reactant, and then they'll ask you, hey, now find me the rate constant, and you'll remember, second order reactant, so I do 1 over, and then you get a linear graph. I mean, in this case it would be 1 over if it's a second order, and then you'd get a linear graph like this, and then you read off of the slope. If it was a first order, then you take ln of A, it's going to be a graph going down, you'd also read off of the slope and get K, so on and so forth. That part makes sense, like that type of question makes sense, how you do it. Now, we have kind of so far ignored the whole point of this. Because now, well actually no, we haven't ignored the whole point. Before when we knew this chemical equation, and we assumed that everything collides at once, figuring out this rate law was easy from experiment. It was easy. But now, even if we know this equation, we don't know the rate law, because we don't know the reaction mechanism, and we have absolutely no idea like how things actually collide. Even if we knew the equilibrium stuff, we still don't know the reaction mechanism to be able to write down these steps and come up with an actual rate law. And that sucks. However, we can figure this out from experiment. And I'm going to, this is from like one of your handouts. I'm stealing stuff that one of your teachers showed to us. Stealing is bad. Okay. So, I mean, if to sue me, I don't care. I guess I'll hopefully. Yeah, I'm just copying a question from one of your handouts. I'm sorry. And you have the following reaction. You have the reaction NO plus H2, and then it's all gas. Gas. Actually, no, I think have I not shown this reaction like last time? Dancing gas?
It's gonna fall on you.
Well, that's fine. I don't really need my fingers, but I play piano, but I can live without that. And you're given the following data. How many? 1, 2, 3, 4, 5. 1, 2, 1, 2, 3, 4, 5. Okay, very good. And this is the initial concentration of NO. This is the initial concentration of H2. And this is the initial rate of reaction. Do you agree? And they managed to, remember how I said it's difficult to calculate rate of reaction directly from the concentration you measure? Well, suppose you did. And suppose it was easy.
Lovely.
And I mean, it is technically like you'll get a vaguely right number. Like you'll get a good enough number to know what's happening. So that's okay. And okay, I'm going to fill in these numbers. 0.001, 0.003, 0.004, 0.004, 0.004, 0.004, 0.004, 0.004, 0.0, and this is like an example of an exam question you could straight up get.
Where did the C? Oh, that's an H.
Well, what? That's
Oh,
an
it's the
H2 bracket, yes. Don't sue me, but like, hopefully stealing this question is like not too bad, that it explodes the school. I mean, these questions are like standard ED questions. I'm just taking these numbers because I don't want to figure out the numbers on my own. Okay.
Can't read those.
What?
0. Which ones? Can you read these?
The left.
The one on the left. 0.001. 0.003, 0.004, 0.004, 0.004. Second column.
Okay.
0.004, 0.004, 0.004, 0.002, 0.001.
Okay.
And the last one is
Okay,
0.
I can read these ones,
Okay,
Thank you.
great.
Wait, what is the last column? You don't have to read the numbers, what's the label?
A rate of reaction. So now for us, like in theory, we could get the rate of reaction experiments. It is possible in theory. You'll have high uncertainty, but like it's doable. It's possible. So all of this data you could actually get from an actual experiment. Yes, people agree with that. Now the question is, we want to use this experiment to find out what this order of each reactant is. People remember order of each reactant are these like powers, right? And if we find out what the powers, the order of each reactant is, right, then we can figure out the, what's it called? Then we can figure out what the rate law is, right? Okay, here we see two reactants, right? How are we going to do this? Whenever you want to solve a question, and then you have some equation related to it, and you want to find something about that equation, it's always useful to write out the equation for your problem. And for each one of these lines, we can write out one equation. And we'll do that. So, here we have what? We know that the rate law, overall, should be some constant times the concentration of NO to some power n. We don't know what that power is. That's the whole point. We want to find out what these powers are. Times the concentration of H2 gas to some other power. We don't know what these powers are. You agree with me, right? On that. However, we know what NO is, we know what H2 is, we know what the rate is. We don't know what the constant is, but we can deal with that. So, actually, I'll rewrite this like at the bottom here. R is equal to, so we know that the equation looks like something like this. This we know. Now using this information, we have to try and figure out what N is, what M is, and what K is. Because we're given what R, N, O, and H2 are in like a single row, right? So for this N, for this concentration of NO, for this concentration of H2, this is going to be the R, right? That makes sense? This is what the data tells us. So, okay, we can then make the following equations. We get that what? We get that R is what? R is 0.020 is equal to K times 0.001 to the power of N times 0.004 to the power of M, right? I just plug these numbers into this equation. Does that make sense to people? What I just did? It's not difficult. We're almost done, by the way. Like, this is the last question we're doing, and then I'm done.
Wait, what are we solving?
We said this is a multi-step reaction, right? So not everything's colliding at once. Or at least we don't know if this is a single-step reaction. So probably not everything's colliding at once. So we don't know what these powers are in our rate law, right? We also don't know what the rate constant is. So our job now is using this data, figure out what the rate law is, what these powers are,
Okay.
and figure out what the rate constant is.
Oh, okay, okay. Just like,
Because if we knew all of this collides at once, we instantly know these powers. We know that the powers are just one. But this doesn't look like it all happens in one step, because like, this looks too complicated. This O has to go to the H. Like they have to like exchange things. And that's weird. Right, so. I'm sorry. This is an H. This is an H. That's an M.
There anything's actually in all of this. No, there's not.
I was like, magnesium, new phosphorus. Anyways,
Okay, and now we can write the same equation, but for this other data. So you get 0.180 is equal to K times 0.003 to the power of N times 0.004 to the power of m. Now, using these two equations, this is already enough to solve for n. And I'm going to, I think, people who have had a certain physics teacher at a certain school would know how to solve this. For the bio kids.
Okay.
For the bio kids, you guys can notice that, hey, this k and this k are the exact same, do you agree?
Yes.
This m and this m are exactly, this 0.004 to the power of m, and this 0.004 to the power of m.
Yes.
Why am I shouldn't be putting square brackets. They don't mean anything anymore. I can just put normal brackets. It's not wrong to put square brackets, it's just confusing. You can't have concentration of a number. Okay, well, I mean, don't worry about that.
What?
If we divide these two equations by each other, what are we going to get? Divide, so this is equation 1, this is equation 2. Divide 1 by 2. 1 by 2. You're going to notice that the stuff with the m's is going to cancel out because it's the same number, right? The k's are also going to cancel out. And you're going to get 0.020 divided by 0.180 is equal to actually, let's do it the other way around. Sorry. Let's divide this one, divide 2 by 1. And then we're almost done. 0.180 divided by 0.020 is equal to 0.003 divided by 0.001 to the power of n. And now we have only one unknown. We have only one variable that we do not know, and we have one equation, one unknown, so we can solve that very easily. How do we solve? What's this number? We can notice that this number is equal to 3. And what's this number? This number is 0.9. No, is it? It's 0.9. No. Or is it just 9? Yes. So okay, we get 9.
Oh.
9 is equal to 3 to the power of n.
My bad.
9 is equal to 3 to the power
Oh,
of n. What's
wow.
n?
Slay. 20.
What's n?
2.
N is equal to 2. Okay, and then in this similar way, look at the data next, right? Why was this possible? Because we had two concentrations for H2 which were the same, and then two concentrations for an O that were different. So the concentrations for an O didn't cancel out, but the concentrations for H2 did. Now if we want to solve for M, we want the stuff with N to cancel out, and the stuff for M to be different so it doesn't cancel out. So we want to have two entries where the concentration of H2 is different, but the concentration of NO is the same. So we can use the same trick. And when we have this, we have two concentrations where NO is 0.004, and then the concentration of H2 is, one is 2, the other one's 1, right? And in fact, I'm not going to write out the full equation because all of us are tired. I'll just write our division of these equations and I'll just solve it directly. It's going to be confusing, I'm just lazy, so I don't care. So we have 0.160 divided by 0.080. That's the rates of these reactions. I'm dividing this one by this one. Rates of this reaction is equal to what? Is equal to k divided by k. That cancels out. And we have NO, so 0.004 to the n, divided by 0.004 to the n. That also cancels out. And we're left with 0.02 to the m divided by 0.001 to the m. So we get 0.002 divided by 0.001 to the m. And now, hey, what's 160 divided by 0.80? That is 2. Is equal to 0.002 divided by 0.001 is also 2 to the power of m, and we get that m is equal to 1. So now we've solved for n, we've solved for m. And now we have our rate law. The only thing we don't know is the k constant. But if we know n and m in this equation, we can just plug them in and solve for k very easily. And now, using this data, having no idea of what the reaction mechanism actually is, what is the slowest step, how to do anything, we've already found ourselves that the rate law is equal to some constant which you can calculate times the concentration of NO squared times the concentration of H2 gas.
Why is the O so tiny?
You're wrong. Well, okay. Does this make sense? And this is a common type of question IBS. Like, I think a question like this has appeared like in all tests. Like, well, all chemical kinetic tests, which is one test. So, that I've had. But yeah, is there anything else I wanted to say? I think there was one last thing. I've been saying it's the last thing for like a while now. Oh yeah, plenty of time. You know, my time is limited by how much storage I have on my phone, which is 128 gigs. So we're good. I can like record many hours of this. Last thing that I want to say. Remember how we drew our energy diagrams that none of us understand, me included. I mean, it's kind of true. I'll erase. Okay, I'll erase this because we actually never use this, but you're supposed to know that, so know that. Actually, this, you know what? Just small tip, at least from personal experience. You know how a lot of the stuff we've done just uses k as just a magic constant and doesn't use this stuff. Like we never really bother with most of this.
Should we forget it?
No, definitely not because there are any questions about it. But this is a great extension for a lot of your IAs. Find a way to tie in that to chemical kinetics.
So if we're using K in class, it'll be mostly for that.
It mostly is just going to be some constant that you don't know and you have to like find something. Sometimes they like do something to this, but I don't really remember all that many questions that actually use this. It's something you just kind of know that, hey, this is kind of how, oh, there's a thing I forgot to say. You know why it makes sense for this to be negative EA over RT? Like e to the power of negative EA over RT? Remember last time, I very vaguely talked about this thing called the Maxwell-Boltzmann thing? The Maxwell-Boltzmann distribution? Yeah. What did the Maxwell-Boltzmann distribution, that's good. What did the Maxwell-Boltzmann distribution tell us? It told us the following thing. It was some graph that looked vaguely like this, right? And it told us that if this is our kinetic energy, this way, right? Then if you calculate this area, this area is going to tell you the number of particles that have energy less than this number, right? Now if you remember, in our rate law, this was supposed to be the percentage of successful collisions, right? So the percentage of collisions that have sufficient energy to stick together. And if you remember, this looked something like e to the k times e to the power of negative e to the k divided by r something. That looks kind of similar, right? You have an e to the negative k here, you have an e to EA, different activation energy, but
They're basically the same.
no, they're very different. An activation energy, say this is your activation energy, tells you like, if you know the activation energy, you can calculate the area here, and then you know the percentage of particles that can't collide successfully. And actually, maybe like if you do compute this area directly, you do get this, something like that. And the idea is this most likely comes from something that looks like a Maxwell-Boltzmann diagram. And it's okay, I've now motivated by this looks kind of like this. That's the best I can do. Now remember that the Maxwell-Boltzmann diagram only works for ideal gases. But this works for like everything. However, an ideal gas, a solid, a fluid, aren't they all the same? I mean, actually, like thinking about this diagram, like helped me quite a bit, like understanding things that aren't gases, but it's good as like intuitive understanding. Almost. Last thing.
Oh, okay.
Like last thing. About the energy diagrams. Okay, the weird energy diagrams. Okay, one fact. So before we said our energy diagram looks like this. Right? Where this is like, it actually reacts at this point and then loses off some energy. But now we've learned that reactions like this one can have multiple steps. That doesn't look like it has multiple steps. So then you can have like multiple step diagrams. And then you can have something like this.
It's like the cyclins.
Yes, you just, this is the first step, that's the second step, that's the first step, second step, third step. That's it.
Oh, okay.
There's nothing to it. And then you can figure out once again using Hess's law. You have like 3 steps. 1 step, step 2, step 3. If you know the activation, so the activation energy for each step is, I think, this distance, right? But then this distance here is the enthalpy for the first step. Then this distance here is the enthalpy for the second step. And then this distance here is the enthalpy for the third step. And if you add them all together by Hess's law, as we know, you'd get the enthalpy, like overall enthalpy, which is, I mean, looks like they're on the same level, but if I did like that, if you add all of them up together, then this would be, if you added all of them up together, you'd get this enthalpy of the entire thing. And that's just Hess's law, right? Like I said, Hess's law is if you do a bunch of steps instead of doing the entire thing at once, if you add the enthalpy of those steps, you still get the enthalpy of the entire thing. And that's the idea. When you have more steps, you just like draw more of these things, and that's it. I don't know. You might be given like a reaction mechanism with enthalpies and asked to like draw this, but it's not too complicated. Like it's the same thing as the one with the other one. It's just that like imagine you have a new enthalpy, a new energy diagram starts when like this first step. Then you have the energy diagram for the second step, starting off where you left off. And you have the energy diagram for the third step, starting where you left off after the second step. It's to just think of it as like 3 energy diagrams put together. And I think that's all. Oh wait, no, yeah, I said that.
Wait, what are you adding up for the enthalpies? Like
For the enthalpies, if you have the entire reaction is you doing 3 steps together, then the enthalpies of each and single steps together gives you the enthalpy of the entire reaction.
Oh, okay.
I mean that was all of last time. Yes. Hi.
So are we ever gonna have like a situation where they give us like the last equation you're talking about?
Which one?
Like the like the r equals like negative. Wait, hold on. The slope thing.
So what equation would you be given?
I don't know. Like we were just talking about like you have a scenario with like a certain chemical and like let's say
One chemical or 2 chemicals colliding, and we found the functions for the concentration over time.
Yeah.
Yes.
Yeah.
You would never be given those functions. You might be given you wouldn't be given the function. You would be given like a plot or like points of concentration to time. That you can be given.
Oh, and then you would have.
And then you would have to find the K constant out of that.
Okay.
But sometimes they give you like a more complicated question, where they give you a reaction they give you this information for that reaction, and then they also give you like the concentration of a reactant over time. Actually, no, from here you can already calculate it. Yeah, they just tell you this is like a first order or a second order reactant. Here's the concentration of it over time. If it's a first order reactant, you take ln of all the points and get K as the slope. If it's second order, you do 1 over it. And if it's 0th order, it's already over.
Okay.
Is this in the data booklet?
What is in the...
The long, like first order, second order.
No.
Oh.
You just have to remember, like 0th, first... That's the annoying part. Here, at least, I gave you a maybe not obvious way, if you're not like comfortable with calculus, way of how to solve it. But in IB, you just have to memorize like what you do for which case. Here, if you spend a little bit of time at home thinking about this, you would be easily able to like integrate yourself. Like it's actually not that difficult. Like if you just spend some time at home, think about it. So if you're stuck on an IB test and you don't remember, this is a secondary reaction. Do I like take ln or do 1 over it? Or is that already a straight line and I'm just blind? If you don't remember, you can always refigure it out on your own, rederive it, and so on and so forth. But yeah, IB just expects you to remember what the graph looks like and what to do with it if you have to.